it is highly improbable that a dog would be electrocuted solely by step potential on concrete. Step potential refers to the difference in electrical potential between 2 points on the ground, separated by the distance of a stride, either by a person or an animal. The voltage gradient, which is the change in voltage over a distance, is typically at its highest near the source of the electrical fault and diminishes as you move further away. For the dog to have been electrocuted in this scenario, the voltage gradient on the concrete would need to be sufficiently high to overcome the dog's body resistance. A typical dog's body resistance is approximately 1000 ohms. Therefore, the voltage gradient would have to reach at least 100 volts per meter for electrocution to occur. While it is possible the dog came into contact with a live wire lying on the ground, it is more plausible that another source of electricity was the cause, such as a fallen power line or a defective electrical outlet. The presence of salt and sidewalk, as mentioned in the news article, might have contributed. Salt is known to conduct electricity, and a damp sidewalk would further enhance its conductivity. However, it is unlikely that salt and the sidewalk alone would generate a sufficient electrical potential to cause death. To understand this further, let's consider the factors at play. Firstly, the amount of current required to cause electrocution. Secondly, the resistance of the path that the current takes through the dog's body. Thirdly, the voltage necessary to drive that current through that resistance. The severity of an electric shock depends on several factors, including the amount of current flowing through the body, the path of the current, the duration of the shock, and the frequency of the current. Even small amounts of current can be dangerous. For example, currents as low as 1 milliamp can be perceptible, while currents around 10 milliamps can cause muscle contractions, making it difficult to let go of the source. Currents of 100 milliamps or more can be fatal. The path the current takes through the body is also crucial. If the current passes through vital organs like the heart or brain, the consequences are much more severe. The duration of the shock also plays a role. The longer the exposure, the greater the damage. Alternating current, abbreviated AC, is generally considered more dangerous than direct current, abbreviated DC, at the same voltage and amperage. This is because AC can cause tetany, a sustained muscle contraction that prevents the victim from releasing the electrical source. Now let's consider the concrete sidewalk. Concrete is not a particularly good conductor of electricity when it is dry. However, its conductivity increases significantly when it is wet, especially if it contains impurities like salt. The salt lowers the resistivity of the water in the concrete, making it easier for current to flow. The stray voltage situation could arise from a variety of sources, including damaged underground cables, faulty equipment, or improper grounding. Stray voltage is an unintentional voltage that exists between two conductive objects that a person or animal could simultaneously contact. In this case, the abandoned street lighting circuit is suspected. If the insulation on the underground cable is damaged, current can leak into the surrounding soil and concrete. This creates a voltage gradient in the area around the fault. The voltage gradient would be highest at the point of the fault and decrease with distance. If a dog were to step on the concrete in this area, there would be a potential difference between its front and back paws. This potential difference could drive current through the dog's body. The amount of current that would flow through the dog's body would depend on the voltage gradient, the dog's body resistance, and the contact resistance between the dog's paws and the concrete. The dog's body resistance is typically around 1000 ohms as previously stated, but this can vary depending on the size and condition of the dog. The contact resistance between the dog's paws and the concrete also depends on several factors, including the moisture content of the concrete and the presence of salt or other contaminants. Even if the voltage gradient is relatively low, the current could still be high enough to cause injury or death, especially if the dog is wet or standing in a puddle of water. Furthermore, stray voltage problems are complex and often require specialized equipment and expertise to diagnose and resolve. Utility companies typically use sensitive meters to measure voltage gradients and ground currents. They may also use techniques like ground impedance testing to identify faults in underground cables. In addition to the factors already discussed, there are a few other things to consider. Firstly, the type of electrical system involved. Secondly, the grounding system. Thirdly, the presence of other conductive objects in the area. The type of electrical system can affect the severity of the shock. For example, a 120-volt circuit is generally less dangerous than a 277-volt circuit. The grounding system is also important. A properly grounded electrical system provides a low resistance path for fault current to flow back to the source. This helps to trip circuit breakers and prevent dangerous voltages from building up. If the electrical system is not properly grounded, the fault current may find an alternative path back to the source, such as through a person or animal. The presence of other conductive objects in the area can also increase the risk of electrocution. For example, if the dog is standing near a metal fence or a water pipe, the current may flow through these objects and into the dog's body. In conclusion, while it is highly unlikely that the dog was electrocuted solely by step potential on the concrete, it is important to be aware of the potential hazards of stray voltage. If you suspect that there is stray voltage in your area, you should contact your local utility company immediately. They will be able to investigate the situation and take steps to mitigate the risk. Regular inspections and maintenance of electrical systems can help to prevent stray voltage problems. This includes checking for damaged cables, loose connections, and corrosion. Proper grounding is also essential for electrical safety. All electrical equipment should be properly grounded to provide a low resistance path for fault current to flow back to the source. Be aware of your surroundings and avoid contact with conductive objects, especially when the ground is wet. This is particularly important in areas where stray voltage is suspected. Educate yourself and others about the dangers of electricity. This can help to prevent accidents and save lives. If you see a downed power line, stay away from it and call the utility company immediately. Do not attempt to move the power line yourself. Remember, electricity can be dangerous, but by taking the necessary precautions, you can significantly reduce the risk of electrocution. Now, to get a better understanding of electrical safety, it is essential to familiarize oneself with the relevant electrical codes and standards. These codes and standards provide detailed guidelines for the safe installation and maintenance of electrical systems. The National Electrical Code, abbreviated NEC, is the most widely adopted electrical code in the United States. It is a comprehensive set of rules that covers all aspects of electrical installations, from wiring methods to overcurrent protection. The NEC is updated every 3 years to reflect the latest technological advancements and safety practices. It is important for electricians, engineers, and anyone involved in electrical work to be familiar with the NEC. Some of the key topics covered in the NEC include grounding and bonding, wiring methods, overcurrent protection, and equipment installation. Grounding and bonding are essential for electrical safety. Grounding provides a low resistance path for fault current to flow back to the source, while bonding ensures that all metal parts of an electrical system are at the same potential. Wiring methods specify the types of cables and conduits that are permitted for different applications. The NEC also specifies the minimum wire size for different circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a safe level. The NEC provides detailed requirements for the installation of electrical equipment, such as lighting fixtures, receptacles, and appliances. These requirements are designed to ensure that the equipment is installed safely and correctly. In addition to the NEC, there are other electrical safety standards that are relevant to specific industries or applications. For example, the National Fire Protection Association, abbreviated NFPA, publishes standards for electrical safety in the workplace. The Institute of Electrical and Electronics Engineers, abbreviated IEE, developed standards for electrical power systems. These standards provide guidance on a wide range of topics, including power system protection, grounding, and surge protection. Understanding electrical circuits is fundamental to understanding electrical safety. An electrical circuit is a closed loop that allows electrical current to flow from a power source to a load and back. The basic components of an electrical circuit include a power source, conductors, a load, and a switch. The power source provides the electrical energy that drives the circuit. This could be a battery, a generator, or the electrical grid. Conductors are wires or cables that carry the electrical current. The load is the device that consumes the electrical energy, such as a light bulb, a motor, or a computer. A switch is used to open and close the circuit, allowing or preventing current from flowing. There are two basic types of electrical circuits: series circuits and parallel circuits. In a series circuit, all of the components are connected in a single path. The current is the same through all of the components in a series circuit. If one component fails, the entire circuit is broken. In a parallel circuit, the components are connected in multiple paths. The voltage is the same across all of the components in a parallel circuit. If one component fails, the other components will continue to operate. Ohm's law is a fundamental law of electrical circuits. It states that the voltage across a conductor is directly proportional to the current flowing through it and inversely proportional to the resistance of the conductor. Ohm's law is expressed by the equation volts equals amps times ohms. This equation can be used to calculate the voltage, current, or resistance in an electrical circuit if the other two values are known. For example, if a circuit has a voltage of 120 volts and a resistance of 10 ohms, the current flowing through the circuit would be 12 amps. Understanding Ohm's law is essential for troubleshooting electrical problems and designing electrical circuits. Let's further break down how stray voltage can occur, considering the specifics of an abandoned street lighting circuit. Firstly, insulation breakdown. Secondly, ground faults. Thirdly, inductive coupling. Over time, the insulation surrounding the underground cables of a street lighting circuit can degrade due to factors like soil conditions, moisture, and physical stress. When the insulation breaks down, it allows current to leak from the cable into the surrounding soil or concrete. A ground fault occurs when a live wire comes into contact with a grounded surface, such as a metal conduit or a wet concrete sidewalk. This can create a path for current to flow through the ground, resulting in stray voltage. Inductive coupling can occur when an energized cable runs parallel to a non-energized cable. The magnetic field created by the energized cable can induce a voltage in the non-energized cable, resulting in stray voltage. The level of stray voltage depends on several factors, including the voltage of the circuit, the resistance of the soil or concrete, and the distance from the source of the leak. In some cases, the stray voltage may be low enough to be harmless. However, in other cases it may be high enough to cause a shock or even electrocution. Salt and other contaminants can increase the conductivity of the soil or concrete, making it easier for current to flow and increasing the risk of stray voltage. Therefore, the presence of salts on the sidewalk, as mentioned in the news article, could have contributed to the problem. To further prevent stray voltage, regular maintenance of electrical infrastructure is essential. This includes inspecting and testing underground cables, replacing damaged insulation, and ensuring proper grounding. Utility companies should also conduct routine surveys to detect and mitigate stray voltage problems. These surveys can involve measuring voltage gradients and ground currents in areas where stray voltage is suspected. Public awareness campaigns can also help to educate people about the dangers of stray voltage and how to report potential hazards. This can empower individuals to take precautions and protect themselves and their pets. If you suspect that there is stray voltage in your area, you should contact your local utility company or a qualified electrician immediately. They will be able to investigate the situation and take steps to mitigate the risk. Remember, electrical safety is everyone's responsibility. By taking the necessary precautions, we can prevent accidents and save lives. Let's consider the case of a faulty underground cable feeding a street light. Imagine the cable is buried a few feet below the surface of the sidewalk. Over time, the insulation on this cable has deteriorated due to corrosion and physical stress. As a result, a small amount of current is leaking from the cable into the surrounding soil. This creates a voltage gradient in the soil around the cable. The voltage is highest at the point of the leak and decreases with distance. Now, a dog walks across the sidewalk. As the dog's paws come into contact with the concrete, there is a potential difference between its front and back paws. This potential difference drives a small amount of current through the dog's body. If the voltage gradient is high enough and the dog's body resistance is low enough, the current could be sufficient to cause a shock or even electrocution. The presence of salt on the sidewalk would increase the conductivity of the concrete, making it easier for current to flow and increasing the risk. In this scenario, the dog's wet paws would further reduce the contact resistance, making it even more vulnerable to electric shock. It is important to note that the actual voltage gradient and current flow would depend on a variety of factors, including the voltage of the circuit, the resistance of the soil, the distance from the leak, and the size and condition of the dog. To prevent such incidents, utility companies use specialized equipment to detect and mitigate stray voltage problems. This equipment includes sensitive meters that can measure voltage gradients and ground currents. Utility companies also use techniques like ground impedance testing to identify faults in underground cables. When a fault is detected, the utility company can take steps to repair the cable and eliminate the source of the stray voltage. This may involve replacing the damaged section of cable or installing additional grounding. In addition to the technical aspects of stray voltage, it is also important to consider the legal and regulatory aspects. In many jurisdictions, utility companies are required to take steps to prevent stray voltage problems. They may also be liable for damages if someone is injured or killed as a result of stray voltage. Therefore, it is important for utility companies to have a comprehensive stray voltage management program in place. This program should include regular inspections, testing, and maintenance of electrical infrastructure. It should also include procedures for responding to reports of stray voltage and mitigating potential hazards. Public education is also an important component of a stray voltage management program. The public should be educated about the dangers of stray voltage and how to report potential hazards. This can help to prevent accidents and ensure that stray voltage problems are addressed promptly.